Science thrives on precision, yet it acknowledges an inherent companion, uncertainty. Every measurement, every observation carries a degree of error. Error propagation explores how these uncertainties, like ripples in a pond, spread through calculations. Imagine measuring a planet's distance. Our instruments aren't perfect, each observation contains a margin of error. Now, let's calculate the planet's orbital period using this distance. The initial measurement error affects our calculated period, introducing uncertainty. Error propagation quantifies this ripple effect. It helps us understand how uncertainties in initial measurements impact final results. This awareness is crucial for interpreting scientific findings accurately. In a complex experiment, multiple measurements intertwine to produce a result. Each measurement carries its own uncertainty. As we combine these measurements, their errors combine as well. This can lead to a cascading effect where small initial errors accumulate into significant uncertainties in the final result. Consider determining the age of the universe. Astronomers rely on measuring the distances and speeds of receding galaxies. Each measurement has an error bar. These errors propagate through the calculations, influencing our estimation of the universe's age. Ignoring error propagation is like building a tower on a shaky foundation. The higher we build, the more unstable it becomes. Similarly, neglecting error analysis undermines the reliability of scientific conclusions, especially in fields with intricate calculations. In physics, determining the speed of a particle from its energy and momentum involves multiple measurements. Each measurement has an associated error. Error propagation helps us quantify how these errors influence the calculated speed. Astronomy heavily relies on measurements of faint, distant objects. Determining a star's luminosity involves measuring its apparent brightness and distance. Errors in both measurements propagate, affecting our luminosity calculation. Understanding these compounded uncertainties is vital. It helps us differentiate between significant discoveries and results clouded by measurement limitations. Error propagation ensures responsible interpretation of scientific data. Scientists employ various techniques to minimize error propagation. Using more precise instruments reduces initial measurement errors. Careful experimental design minimizes external influences. Repeating measurements allows for statistical analysis, reducing uncertainty. However, eliminating error entirely is impossible. Instead, we embrace it, quantify it, and factor it into our interpretations. This rigorous approach distinguishes scientific knowledge from mere speculation. By acknowledging and managing uncertainty, we strengthen the reliability of scientific findings. Error propagation isn't about achieving perfect precision. It's about understanding and communicating the inherent limitations of our observations.